Good morning, everyone. Thank you for joining us today. In our last session, we dove into the incredible world of nanofabrication, how scientists actually build things at the atomic level. But that leads to a huge question. Once you make something that small, how do you even know it's there? How do you check your work? To help us unpack all of this, we're joined by our expert guest. Welcome.
Hello, everyone. Thank you for having me. It's a genuine pleasure to be here to discuss this important topic.
It's great to have you. So let's jump right in with the question on this slide, because it really gets to the heart of the matter. If you build something smaller than the wavelength of light, how in the world do you see it?
That is the fundamental problem, isn't it? It's the perfect starting point. You know, every optical microscope you've ever used works by using light to magnify an image. But light itself has a physical limit, something called the diffraction limit. Think of it like trying to measure a single strand of hair with a ruler that only has centimeter marks. Your measuring tool is just too big for the object. When your object is smaller than the waves of light you're using to see it, those light waves literally just bend right around it. It becomes invisible. And that was the brick wall that early nanotech researchers hit. They were trying to create amazing new things, but they were essentially working blind. You see, making something is only half the job. If you can't see it, measure it, and understand it, you can't improve it. This is exactly why the entire field of nanotechnology characterization had to be invented.
And that brings us right here. Characterization isn't just one tool, but as this definition says, a whole suite of them. Can you expand on why this is so foundational? Why is it the essential feedback loop for the whole field?
Absolutely. I tend to think of characterization as the quality control department, the forensics lab, and the blueprint checker all in one. It lets us do three really critical things. First, it's just basic verification. Did my process work? If your goal was to make 10 nanometer gold spheres, characterization tells you that you didn't accidentally end up with 50 nanometer cubes. It's the first, most basic check. Second, it helps us understand the properties, and this is where it gets really cool. We know nanomaterials have these amazing properties. They're stronger, more conductive, have different colors. Characterization is how we connect a specific structure to a specific property. It's how we can say, oh, when we arrange carbon atoms in this pattern to make graphene, it becomes 200 times stronger than steel. We're essentially writing the rule book for this new nanoscale world. And third, it's all about quality control and safety. For any real-world product, from medicine to a new computer chip, you have to be able to make it the same way every single time. Characterization techniques are what make that possible. Without this kind of rigorous analysis, nanofabrication would be like trying to assemble a Swiss watch blindfolded wearing oven mitts. It would just be a chaotic art form, not a scalable science.
That is a fantastic analogy. It's so clear that this is a totally essential part of the process. So for today, it looks like we've got our roadmap laid out. We'll start with that nanoscale blind spot, then look at how we visualize things, figure out their chemical makeup, and understand how they behave before wrapping it all up.
Exactly. I like to think of this as our nanoscientist's detective toolkit. Every technique we're about to discuss is like a different clue. A photo, a fingerprint, a fiber sample. And you really need to put all those clues together to solve the mystery of what a new nanomaterial is and what it can do.
All right, let's get into that first section, the nanoscale blind spot. You mentioned the problem with light, but let's really nail down why our traditional microscopes just can't cut it.
Right, so this blind spot isn't just a technological hurdle we haven't solved yet. It's a hard limit set by the laws of physics. The wavelength of the light we can see is between, say, 400 and 700 nanometers. But nanotechnology, by definition, works with structures from 1 to 100 nanometers. So we're often trying to see things that are hundreds of times smaller than our ruler. No amount of fancy lens making can fix that. To see into the nanoscale, we had to throw out the rulebook and stop using visible light altogether.
This slide states it very clearly. So if light is the problem, what was the solution? What was the big idea that let scientists get around this limit?
Well, the breakthrough was realizing we could use particles instead of light waves. Specifically, we turned to electrons. Now, thanks to the wonderful weirdness of quantum mechanics, we know that particles, like electrons, also act like waves. And the physicist Louis de Broglie showed that a particle's wavelength gets shorter as its momentum gets bigger. The key insight was that if we accelerate electrons with a high voltage, we can give them a ton of momentum, which in turn gives them a wavelength that's thousands of times shorter than visible light. We're talking fractions of a nanometer. By using a beam of these high-energy electrons instead of a beam of light, we could finally get the resolution needed to see into the nanoworld. This was the key that unlocked our first set of major tools, electron microscopes.
That's a brilliant leap in thinking. So we're swapping out photons for electrons. Let's move into our second section here, visualizing the evidence. We're opening up that detective's toolkit, and it sounds like the first tools are these electron microscopes. Where does a scientist usually start when they just want to see what they've made?
The first stop for pretty much any nanoscientist is the Scanning Electron Microscope, or SEM. If you just want to know what your sample looks like on the surface, SEM is your go-to. Its main job is to give you these incredibly detailed, almost 3D-looking images of a sample's topography. It answers those basic but vital questions. Are my nanoparticles spheres or rods? Are they clumped together? Is my thin film smooth or rough? It's the ultimate tool for just seeing a material's shape, size, and texture.
This comparison on the slide is really useful, putting SEM next to another tool, the Transmission Electron Microscope, or TEM. Let's stick with SEM for a second. How does it actually generate those amazingly detailed pictures of the surface?
It's a pretty elegant process. As the name suggests, it scans a very focused beam of electrons across the sample surface in a grid, kind of like how an old tube TV used to draw a picture. When this beam of electrons hits the sample, it knocks some of the sample's own electrons loose. These are called secondary electrons. A detector then collects these secondary electrons. And here's the clever bit. The number of electrons that escape depends on the shape of the surface. An edge or a peak will kick out more electrons than a flat valley. A computer then maps the strength of that signal, pixel by pixel, to build that beautiful, high-detail, 3D-looking image.
So SEM is the master of the surface. But what if the important stuff isn't on the surface? What if it's hidden inside? The right side of the slide points us to TEM. How do we look inside a nanoparticle?
That's the perfect question. And it leads us to an even more powerful and much more complex technique, the Transmission Electron Microscope, or TEM. As the slide shows, everything about it is different. Instead of scanning across the surface, a TEM shoots a beam of electrons that passes all the way through an incredibly thin sample. And that's the key. For TEM to work, your sample has to be so thin that electrons can actually get through it. We're talking under 100 nanometers thick, which is a major challenge all on its own.
Wow, that sounds incredibly hard to prepare. But if you can get the sample that thin, what can a TEM show you that an SEM just can't?
The reward for that hard work is huge. TEM gives you information you can't get any other way. Because the electrons go through the material, you get a 2D projection, almost like a medical X-ray, but with atomic-level resolution. With a TEM, you can see the precise size of individual nanoparticles. Even better, you can directly see the arrangement of atoms in a crystal, what we call the crystal lattice. You can literally see the rows of atoms. This lets you spot any mistakes, any defects or dislocations in that perfect pattern. And these tiny imperfections can have a huge effect on a material's properties. A high-resolution TEM is one of the only tools on Earth that lets us truly see and image single atoms. It's the ultimate look inside.
Seeing individual atoms? That's just incredible. So we've talked about microscopes that use a sense of sight. But this next one, atomic force microscopy, or AFM, sounds totally different. It seems like it uses a sense of touch. How does that work?
That is the perfect way to put it. AFM doesn't see anything. It literally feels the surface. It works by scanning a tiny, unbelievably sharp tip. The point can be just a few atoms wide across the sample. This tip is on the end of a flexible little arm called a cantilever. As this tip moves over the surface, it gets pushed and pulled by the tiny atomic forces between the atoms on the tip and the atoms on the surface. These forces make the cantilever bend up and down, basically tracing the outline of the atoms.
That's amazing. But those movements must be impossibly small. How do you even measure a deflection that tiny and turn it into a map?
This is the really ingenious part. To measure that tiny movement, a laser is bounced off the top of the cantilever and onto a detector. Even a nanometer scale bend in the cantilever causes a measurable change in where the laser spot hits the detector. So as the tip scans across the surface, a computer records that laser's movement and uses it to build a true three-dimensional, high-resolution map of the surface, atom by atom.
That's just brilliant engineering. So what are the big advantages of using an AFM instead of an electron microscope? I've also heard it can do more than just map the shape.
AFM has some game-changing advantages. The biggest one is that electron microscopes need a high vacuum to work, but an AFM can operate almost anywhere, in the air or even completely submerged in liquid. This is huge because it means we can look at samples in their natural environment. We can image biological things, like DNA or even living cells as they function in a liquid. You can literally watch biology happen in real time. And you're right, it's so much more than a mapping tool. You can change the tip to measure all sorts of things. You can poke the surface to measure stiffness or use a conductive tip to map out electrical properties. It's an incredibly versatile instrument.
Okay, so we can see them, feel them, and get these amazing images. But a picture doesn't tell you what something is actually made of. That brings us to our third section, uncovering the chemical fingerprint. How do scientists get past the image and figure out a material's chemical identity?
This is a really important shift. We're moving from shape to composition. It's like the difference between having a photograph of someone and having their DNA profile. The photo tells you what they look like, but the DNA tells you who they fundamentally are. To do that, we need techniques that probe the very nature of the material itself, its crystal structure, and its chemical bonds. This is how we confirm what we've actually made.
So let's start with that fundamental identity. How do you figure out the precise, ordered arrangement of atoms? This quote mentions getting a unique fingerprint for it.
This quote is talking about one of the oldest and most powerful techniques we have, X-ray diffraction, or XRD. Its main job is to determine a material's crystal structure. Most solid materials are crystalline, meaning their atoms are arranged in a nice, orderly, repeating 3D pattern. XRD works by shining a beam of X-rays at the sample. Because the wavelength of X-rays is about the same as the distance between atoms in a crystal, the atoms act like a perfect diffraction grating. The X-rays scatter off these planes of atoms, and at very specific angles, they interfere constructively, creating a strong signal. By measuring the angles and intensities of all these diffracted beams, you generate a pattern of peaks. And just like the quote says, that pattern is a definitive, unique fingerprint for that material's specific crystal structure. No two different crystal structures will ever give you the same XRD pattern. It's the gold standard.
That sounds incredibly definitive. Now, this slide shows two other techniques under the umbrella of spectroscopy, and they both seem to use light, but in different ways. What can we learn from the first one, UV-vis spectroscopy?
UV-vis is a much simpler but still very useful technique. It works by shining light through a sample, usually a liquid, and measuring how much light gets absorbed at each wavelength. Its real power in nanotech shows up with materials like gold and silver nanoparticles. With these materials, something cool happens called surface plasmon resonance. The electrons in the metal oscillate in response to the light, and the exact color of light that gets absorbed depends very strongly on the nanoparticle's size and shape. This is why a vial of 10 nanometer gold particles looks ruby red, but 50 nanometer gold particles look purple. The color is a direct result of their size. UV-vis measures this color precisely, giving you a very fast and cheap way to check the size and quality of your nanoparticle batch.
So UV-vis is about what light gets absorbed. What about the other one, Raman spectroscopy? The table says it looks at light scattering to get a more detailed chemical fingerprint.
Yes, Raman gives you a much deeper chemical profile. It's a bit more complex. It also uses a laser, but it's looking for something very subtle. Most of the light that hits a sample just bounces off at the same color. But a tiny, tiny fraction of it, maybe 1 photon in a million, actually interacts with the chemical bonds in the material and scatters off with a slightly different energy, a different color. That tiny energy shift corresponds to the natural vibration of the chemical bonds themselves. Think of every chemical bond, like a carbon-carbon bond, as a tiny guitar string that vibrates at a specific frequency. Raman spectroscopy essentially plucks all these molecular strings with a laser and listens to the notes they play. The result is a spectrum that acts as a rich chemical fingerprint, revealing incredible detail about composition, molecular structure, and even things like stress or defects in a material. It's absolutely essential for materials like graphene or carbon nanotubes.
That's a great way to explain the difference, so we can see them, feel them, and identify them. But I've always heard that at the nanoscale, the surface is everything. That leads us to our next section, understanding surface behavior. Why is the surface so incredibly important at this tiny scale?
It's all about geometry, and it's one of the most fundamental concepts in nanotech. When you shrink an object, its volume goes down by the cube of its size, but its surface area only goes down by the square. This means the ratio of surface area to volume just explodes. For example, if you take a 1 centimeter cube and chop it up into 1 nanometer cubes, you increase the total surface area by 10 million times. All of a sudden, a huge percentage of your material's atoms are now on the surface. And those are the atoms that interact with the outside world, with liquids, with other molecules, with cells in the body. So the properties of that surface, its charge, its reactivity, start to dominate the material's entire behavior.
That makes perfect sense. So if the surface is so vital, how do we measure its properties? The first one here is zeta potential, with this benchmark of plus or minus 30 millivolts. So if I have nanoparticles floating in a liquid for something like a drug delivery system, what stops them from just clumping together? How does this number help?
You've just described the exact reason for this technique. Zeta potential measures the electrical charge on the surface of nanoparticles when they're in a liquid. This measurement is the best predictor of whether that suspension will be stable over time. That value you see, plus or minus 30 millivolts, is a general rule of thumb. If the particles have a strong charge, either very positive or very negative, they will repel each other, kind of like trying to push the north poles of two magnets together. This repulsion is what keeps them from sticking together and clumping up. If your zeta potential is close to 0, that's a huge red flag. It means your nanoparticles are probably going to aggregate and fall out of the solution, which could be a disaster for the application.
So zeta potential is like an insurance policy for stability. What about the surface area itself? This number on the slide is mind-boggling. 2,500 square meters per gram? That's like taking a single gram of powder and unfolding it to cover half a football field. How is that even possible to measure, and why would you want that much surface area?
That number really puts it into perspective, right? The technique we use to measure this is called BET analysis. It basically works by seeing how much nitrogen gas will stick to the surface of the material at very cold, liquid nitrogen temperatures. You put your sample in a chamber and introduce small, known amounts of nitrogen. The instrument measures exactly how many gas molecules it takes to form one single layer, a monolayer, covering the entire surface. Since you know the size of one nitrogen molecule, you can calculate the total surface area. And this property is absolutely critical for some of the most important applications. In catalysis, more surface area means more spots for chemical reactions to happen. In batteries, it means more space to store energy. In filters, it means more capacity to trap pollutants. In all those cases, performance is directly tied to surface area.
It's amazing how you can quantify these completely different but equally crucial properties. This brings us to our final section, building the full profile. We've talked about this whole toolkit, with each tool giving us a specific piece of the puzzle. Is there ever a single best method to use?
That's the most practical question you could ask, and the answer is a very firm no. There is no single magic bullet technique. Each method we've talked about gives you a different, complementary piece of the story. Each one has its own strengths and its own blind spots. If you rely on just one technique, it's like a detective trying to solve a crime with just one blurry photo. You'll get an incomplete and probably misleading picture. Real understanding only comes from putting all the clues together.
So this slide really is the detective's toolkit. It's not about picking just one, but knowing how to combine them to build a strong case.
Exactly right. A good characterization plan uses several of these techniques in a logical order. So let's say we're developing a new nanoparticle catalyst. First, we'd use SEM to get a quick look. Did we make particles of the right size and shape? Then we'd use TEM to look inside them to check for any crystal defects that might ruin the catalysis. After that, we'd use XRD to get the definitive fingerprint and confirm we made the exact crystal structure we wanted. We might use spectroscopy to check for any chemical junk on the surface. And finally, because catalysts need huge surface area, we'd run a BET analysis to measure it. At the end, you don't have just one data point, you have a complete, robust profile of your material. You've built the full case, clue by clue.
And this final quote just says it all. Fabrication and characterization are the two legs that the entire field of nanotechnology stands on. They're locked in a feedback loop. You make something, you characterize it to see what you really made. Those results tell you how to change your fabrication process, and you repeat that cycle over and over, getting closer to what you want. So if fabrication is the art of building at this tiny scale, characterization is the science of actually seeing and understanding what you've built. One cannot exist without the other. I have one last practical question. This all sounds incredibly advanced and, I have to imagine, very expensive. Where does this work actually get done? That's a great question. This isn't the kind of equipment you just have sitting in a normal lab. A top-of-the-line transmission electron microscope can cost millions of dollars and needs its own special room protected from any vibration or magnetic fields. Because of that, these instruments are usually housed together in large, centralized facilities at major research universities or national labs. They're the hubs where scientists from all over, from both academia and industry, can come to access the tools and the experts who run them that they need to push the science forward. That's a perfect place to wrap up. So, to summarize, we learned today that nanotechnology simply cannot exist without characterization. To get past the limits of light, scientists need a powerful toolkit. We have electron microscopes like SEM and TEM to see surfaces and internal structures. We have tools like AFM that can literally feel the atomic landscape. To find a material's identity, we use XRD for a crystal fingerprint and spectroscopy for a chemical one. And to understand how they'll actually work, we measure surface properties like charge with zeta potential and area with BET. Most importantly, as you just explained so well, no single technique tells the whole story. A complete picture only comes from combining all the clues from this advanced toolkit. Thank you so much for walking us through that.
It was my pleasure. It's a field that's truly essential for so much of our technological future.
And for everyone listening, be sure to join us for our next session, where we'll build on this and explore the properties of nanomaterials, looking at why these materials act in such unique and powerful ways. Thank you again to our guest, and thank you all for tuning in. To continue exploring the frontiers of technology, be sure to subscribe to our channel, Tech AI and Beyond.